Hello friends, this is part 2 of solution to the electricity and magnetism paper C-3 of second semester BSc second semester physics, Dibrugarh University, 2023. Right. In the first part we have solved question number 1. We have solved question number 1, all the multiple choice questions. Now we're going to solve from question number 2a, question number 2a, 2b, 2c, then 3a and 3b. Okay, we're going to solve these questions, right? And remaining questions will be solved in the next part. Okay, so before we start, please subscribe the channel, hit the thumbs up button, also hit the bell icon so that you get notified when new video will be uploaded. Okay, so now let's start. Now let me start with question number 2a. What is mean by electric flux? Give its SI unit. So let me write the definition of this. Now first let me explain what does it mean, electric flux. Suppose we have a surface. This is a surface. This is surface in an electric field. This is the electric field, suppose, so which is not necessarily to be uniform. Okay, this is the electric field. These are the field lines. Okay, electric field. So, and let me consider this surface. Okay, so let me write these things first. So we have considered an arbitrary surface. This is the arbitrary surface in the electric field E. Okay, its surface area is suppose S. I have taken S is the surface area. Okay, the surface is S, and let us consider a very small portion, ds. This area is suppose ds. Now you see, let me take this as the area vector. Now if you have a surface, suppose this is a surface, then what will be the area vector? So if you now you say this is the right side, this is the left side of the surface. This is the left side, this is the right side of the surface. If you take the area vector of the right side, face on the right side, then this should be in outward direction normally from the surface. Okay, so that's how we used to take area vector. So this is suppose this area is very small area ds, and this is its area vector is ds vector. Okay, we have considered that way, and it makes angle theta, right? It makes angle theta with the electric field, suppose. Then what happens, let me clean these things. Then you see, let me write this surface is divided into very small surfaces, elementary surfaces, or you can say pits. Okay, let me write first. So the surface is divided into elementary pits of can be represented by the vector ds vector, right? So that's how. Now you see, so to find the electric flux, we're going to take the component which is normal to the surface, right? That means which is along the area vector. Okay, if this is the area vector, this is the direction of the area vector, this is the electric field, right? So here you see this is the area vector ds. So we're going to take the component of E along the area vector, right, which is normal to this surface. Okay, so area vector is perpendicular to the surface, right? And so what will be the component of E? Now you see this E component, this component of E will be because here you see this is the electric field E, and this angle is theta, so this component will be E cos theta, right? E cos theta, right? So now here you can see this E cos theta ds, product of this area and this component, gives the flux through this small pitch. Okay, this is small area, so which can be written as E dot ds, right? You see, dot product of two vector, a vector dot b vector, that's going to be a b cos theta, right? So here we have, so you can write this cos theta here. You can see, you can write this way. You can write E cos theta ds as E ds cos theta, right? And that's going to be equal to E dot ds. So it represents, this dot product represents flux through this patch. Okay, this small area, right? So what we can write, the dot product or the scalar product E dot ds, E vector dot ds vector, E vector is the electric field, right? The ds is defined as the electric flux through the patch. And if you want to find the flux through the entire surface of surface area S, then it is given by the flux. Let me write it in black ink. The flux through the entire surface is phi, and this is through this small pitch, right? This is the flux through this small pitch, and if we integrate it, we're gonna get the flux through the whole surface, right? So integrating, so we have to use the surface integral here. S, this is the area, E dot ds. So this is the flux through the entire surface. So hope you have understood this. The SI unit, so where should I write? Just wait. Its SI unit is, let me write here, Newton meter square per coulomb. Newton meter square per coulomb. This is the SI unit of electric flux. So hope you can see it. Let me write here. Its SI unit is Newton meter square per coulomb. So this is the SI unit of electric flux. So now let's move on to the next question. Our next question is, by applying Gauss theorem, find the electric field due to uniformly charged spherical cell at an external point. That means it should be outside the point should be outside the cell, spherical cell. Okay, so in order to solve this, by applying Gauss theorem, find the electric field due to uniformly charged thin spherical cell at an external point. So let us draw a sphere here. This is a sphere, and suppose it is positively charged, and charges are continuously distributed over its surface. Let me consider that way. And its radius is, suppose, capital R. Let its radius be capital R, and we have to find the electric field at a point which is outside the sphere. Okay, this is outside the sphere, and this point is, suppose, P. Let me take this point is P, and in order to apply the Gauss law, let us consider another concentric sphere through this point P. Okay, this is called Gauss surface. This is called Gauss surface, right? We used to say this is Gaussian surface, right? This is Gaussian surface, simply. just wait. This is Gauss surface. So this is the Gaussian surface and its radius is suppose small r. Now we are considering the condition small r greater than capital R, right? So now you see, let us consider that let us consider a thin spherical cell of radius capital R with a positive charge. Instead of writing this way, write the complete word positive, okay? In example, positive charge Q distributed uniformly on the surface, on its surface. So let me take that way. Okay, we are to find electric field E at P. We are to find electric field E at P, right? At P we are going to find the electric field. Okay. So let us draw a spherical Gaussian surface through P of radius small r. Here r is greater than capital R. Okay. So by Gauss law, here you see this will be okay. By Gauss law, the electric flux through this Gaussian surface that's given by integration E dot ds. According to Gauss law, it must be Q enclosed by epsilon naught, right? Q enclosed by epsilon naught. This is according to Gauss law, right? Now you see here, this epsilon naught represents permittivity of free space, right? And here ds, here electric field is constant, it can be taken outside the integral, and integration of ds, right? Integration of ds, that is nothing but the area of this sphere. So that's going to be the area of this sphere. So here you can assume this way that so let us assume a very small area element ds here. So its area vector, so here you see this is the point P, and this area vector of ds is this ds vector along this direction. Okay, so if you integrate this, then you're gonna get the whole area of this Gaussian surface. So you can write here that integration ds is, so area of this sphere, that's gonna be equal to, so this is equal to 4 pi small r square, because small r is the radius of the Gaussian surface. So if that is the case, then what we can write from this relation, we're gonna obtain that this E vector. So instead of integral ds, we're gonna write 4 pi r square, right? So here you see, this is a scalar quantity. This is dot product, so it's gonna be scalar quantity. So you can write here simply E only, right? You can write simply E. That's gonna be q by epsilon naught, q by epsilon naught, and this is equal to this implies E is equal to 1 by 4 pi r, or here you can write 1 by 4 epsilon naught q by r square. That's what you can write. So this is the answer. Okay, so hope you have understood this. This is the required result. So this is electric field due to a spherical cell at an external point, right? So hope you have understood this. Now let's move on to next question. Now we are going to solve 2c. Here, obtain the expression for potential due to electric dipole. Here we have two parts. Then we have to show that electric potential at any point on the equatorial line of a dipole is 0, right? So let us first obtain the expression for the potential due to an electric dipole. So let's start here. I'm going to solve this question. Pause the video and note the question first. So here 2c answer. So what do we need to find? Electric potential due to a dipole, electric dipole. Okay, so how to do that? An electric dipole. Okay, so here we're gonna solve this question first. This is 2c, question number 2c. Okay, let us consider a dipole consists of two charges separated by a distance, suppose d. Here let us assume two charges. Just wait. Okay, so here we have a negative charge, negative q, and we have positive charge here, positive q, and these two are separated by a distance d, very small distance d. And here suppose we need to find the electric potential at a point P, suppose. Okay, at the point P, and we have the origin here, which is at the midpoint of this line joining q and positive q and negative q. Okay, so let me do one thing. Instead of d, let us take it at 2d, so we can consider this is d, right? This is d and this is also d, so let us take that way, right? So here you see that the position vector with respect to the origin O, position vector of P is r. So this is suppose r, right? This is r. Let me write here. This is the position vector r, right? Just wait. Let me write this here. This is the point P, suppose. Okay, here we need to find the electric field. So now you see, now let us consider an electric dipole consists of electric charges minus q and plus q, right? Consist of electric charges plus q and minus q separated by a very small distance 2d, suppose. And here you see minus q is at A and minus q is at B. Minus q is at A, plus q is at B. Let me take that way, and OP is equal to R. This is equal, this length is R, and which is very greater than 2D, right? So now you see, as we had drawn B perpendicular BB dash to this side, this perpendicular, right? Here we have mentioned these two are perpendiculars. So, and here this angle is theta, this angle means this one. Here this angle is theta, right? If this is theta, right? If this is theta, then this side must be the base and this side must be the perpendicular. So let me make it larger. Okay. So this is B dash, this is right angle, so it's gonna be the hypotenuse, right? And this is gonna be the base if this is theta, and this is gonna be the perpendicular. So here it is O, this is B. So from this triangle, what we're gonna have? From this triangle, we're gonna get you see, cos theta is equal to base is OB dash by hypotenuse is OB, right? And OB, this is OB, this part you can see in this diagram, OB is nothing but D, right? So OB is equal to D, so OB dash by D, so which implies OB dash is equal to D cos theta, right? So you're gonna get that. So here, so that is why we can write PO minus D cos theta, right? We can show P minus D cos theta. So here one more thing, let me clean the 6 first. Okay, just let me write here properly, PO minus D cos theta. Now here let me tell you one more thing. This length of this PO, right, here we have mentioned length of this PO or OP is R. So that's why instead of writing PO, you can write R here. Here also you can write R. Okay, that's the thing that what we have got. Now potential due to the charge minus Q, this charge minus Q charge at P. So how to find that? Now you see, let me write potential. So let me use another ink here. Potential due to minus Q at P. So let me write this one as V minus. Okay, so that's going to be equal to minus 1 by 4 pi epsilon naught, or you can write 1 by 4 pi epsilon naught due to minus Q charge, and what going to be the distance here, that is AP, right? Due to this minus Q charge, we are trying to obtain the potential at P. That's why the distance AP should be taken. So here we have already got AP is equal to R plus D cos theta. So you're going to write AP is equal to R plus D cos theta. So that's going to be equal to minus 1 by 4 pi epsilon naught Q by R plus D cos theta. That's what we're going to get, right? So this is V due to negative. Okay. So let me copy this and let me go to the next slide. So let me copy this one. Here we have got the potential at P due to minus Q charge, and let me copy the diagram as well. So this is going to be crucial for us. Okay, so here you can see. Now let us find the potential at P due to positive charge, right? Potential due to Q q positive charge at p. So what going to be the potential? So let me write this one as V positive. So that's going to be 1 by 4 pi epsilon naught q positive by BP. Right, here we're going to the distance from q positive is BP. Distance between P and positive charge is BP here. So, and we have got BP is equal to, let me go to previous slide. So here you can see we have got PB or BP same thing, that is equal to R minus D cos theta. So let me write here 1 by 4 pi epsilon naught Q by R minus D cos theta. That's what we have got. So what going to be the net potential at P? So therefore net potential at P due to the dipole that is V is equal to V negative plus V positive, right? V negative represents potential due to negative charge and V positive represents potential due to positive charge. So hope you have understood this. So let me write here V minus plus V plus. So let me represent that way. So if we add these two, then what are we going to get? Right. Here you can see that we can take this quantity common, right? 1 by 4 pi epsilon naught is taken common, and within bracket we're going to have minus q by r plus cos theta, and here plus q by r minus cos theta, right? That's what we're going to have. So now let's take LCM, and then we're going to write the D here. That should be D cos theta, right? So now if we take LCM, then what we're going to have? 1 by 4 pi epsilon naught. So if you multiply these two to take LCM, and that's going to be equal to r square minus d square cos square theta. And then in the numerator we're going to have minus q into r minus minus plus q into d cos theta, q into d cos theta, then plus q into this qr plus qr qd cos theta, right? So here plus qr minus qr gone. So here we're going to have 1 by 4 pi epsilon naught 2 q d cos theta divided by r square minus d square cos square theta, right? That's what we're gonna have. Okay, now you see, as d is very smaller than r, so neglecting d square, right? Neglecting d square cos square theta. So if we do that, then what we're gonna have? Then we're gonna have v is equal to 1 by 4 pi epsilon naught q into, we can write 2qd as q into 2d cos theta by r square, right? So q into 2d, that is nothing but the dipole moment of the electric dipole. If there are two charges minus q and plus q, and they are separated by a distance 2d, then the dipole moment is given by p is equal to q into 2d, right? So hope you know these things. So that's why we can replace q 2d by the term dipole moment p. So therefore this v gonna be equal to 1 by 4 pi epsilon naught 4 by epsilon naught p cos theta divided by r square. That's what we're gonna have, right? So hope you have understood this. And this is nothing but electric potential due to a dipole. Electric due to a dipole, right? So now let me copy these things, and there is another part in this question. Let me go to the question again. So here you see, we need to show that the electric potential at any point on the equatorial line is 0. Now you see, suppose, so this is the potential at P, right? For this diagram, right? For this diagram at P, this is the potential, right? So what if the potential as the at equatorial line, this is minus q, this is plus q, this is P, this is the 0 at equatorial line, then what you're gonna get? This theta gonna be equal to 90, right? If P is at is on the line, on the equatorial line, then theta will be 90. Therefore potential at P on the equatorial line is V is equal to 1 by 4 pi epsilon naught P cos, here instead of cos theta, here we're gonna write 90 by r square. Now remember one thing, this P is dipole moment, and this is point, this is the capital P is the point here. This is small p represents the dipole moment. I have written or not here, so please mention here. Let me mention one thing here. This is dipole moment, P is equal to Q into 2D, right? Let me mention. So just let me cut this one, and here you see this expression is the expression of electric potential due to a dipole, right? So from here, this is the answer to the next part of the question. So cos 90 is 0, that's why this whole thing gonna be 0. So that's why V is equal to 0. So this is the second part of this question. Here you see this one, so that electric potential at any point on the equatorial line is 0. So that is what we have shown here. This is proved, right? So hope you have understood. And the first part is this. So this is the expression. So pause the video and note it down. Now let us solve question number 3a. So here you see, what do you mean by electrical potential energy of a system of charges? Okay, then we need to derive an expression for this, and also we need to show that energy density is given by this, right? So now let me start with the explanation. What does electrical potential energy of a system of charges? Okay, so let me go to the new slide. Here is the answer, that what does it mean? Electrical potential energy of a system of charges is defined as the work done, it is defined as the work done to bring the charges of the system from infinity to their respective positions, that means suppose we have a system of charges here, q1, this is q2, and this is q3, and here you say this is q4. Okay, q4 with respect to origin O, their positions vectors are supposed respectively r1 and r2 and r3, so on. Okay, so what will be the energy, electrical potential energy of the system of these charges? So that gonna be the sum of work done that required to bring each and every charge from infinite to their respective positions. That means wherever they are at present. Okay, to bring to bring them to these positions from an infinite. So how much work should be done? Suppose for q1 we have done w1 work done, q2 we have done w2 amount of work, and q3 we have done, suppose to bring it from infinity, we have done w3 amount of work. Then sum of all those work done, that's going to be the electrical potential energy of the system of this charge. Okay, so hope you have understood this. Now let us try to obtain an expression. Suppose we have a system, so let me consider this coordinate system here first. So this is x, y, and z, and this is the origin. Say this is the origin. So first we want to find the energy of this charges, system of charges. Suppose up to qn we have, suppose n number of charges. This is q2, this is q3, and so on. Okay, so this is the position vector r1, and this is the position vector r2, and so on. We're gonna get n number of position vectors for n number of charges, rn, suppose. Let me take that way. So now you see work done to bring a charge. Here you see. So now how to explain it? Let me tell you something. So we're gonna bring these charges from infinity one by one, right? Initially we have this situation only. This is the origin, right? There was no charge, there is no charge, right? First we have to bring q1 from infinity to this position vector r1, represented by the position vector r1. And as initially there was no electric charge, so that's why no electric field, and as there is no electric field, we don't need to do any work to bring q1 from infinity to this position vector r1, right? But to bring the next charge q2, we have to do work against the electrostatic force that occurs due to the electric field due to this q1 charge, right? So similarly we have to do work to bring q3 as well, and we're gonna add all those work done, all those amount of work done to bring those charges to these positions. Okay, so now you see, let me write one by one. Now let us assume a system of n charges q1, q2, qn with position vectors r1, r2, up to rn respectively, right? Now electric potential energy of the system of this system of charges is equal to the total work done to bring all the charges from infinity to their respective positions. Right. So let us consider the situation. Right. Let us consider the situation when there is no charge initially in this region. Right. Now just pause the video and note these things, and let me go to the new slide. Okay. Now you see, let us consider this situation. In this region there is no charge, right? In this region there is no charge. Okay. First we are going to bring Q1 charge from infinity to the position R1. So we are to bring the Q1 from infinity to the position R1, right? So as there was no charges before Q1 is brought to the position R1, right? So therefore work done to bring Q1 from infinity to R1 is W1 is equal to 0, right? So now you see, now we have got Q1 here. Now we are to bring Q2 from infinity to the position represented by R2. This is R2 position vector, right? We are to bring this R1 this is Q1 charge, and this is at this position R1, right? So this is R2 position vector of this Q2 charge. We are to bring this Q2 here. So now you see, so here you see, first in order to find the work done to bring this one to this point, first we are to find the potential due to this Q1 at this point, because work done will be given by potential due to Q1 charge, that is V1, into Q2. That's going to be the work done to bring Q2 to this position, right? So here you see, let me clean these things first. Okay, so here you see, so let me write this distance between these two charges be suppose R12. Let me represent it by R12. Okay, so R12. So now you see potential, electric potential at R2 due to Q1 is that going to be given by V1 is equal to 1 by 4 pi epsilon naught Q1 by R12, right? We know that potential due to potential at a point P due to a charge Q is given by, if this distance if the distance of this point from this charge is suppose R, then here the potential is given by 1 by 4 pi epsilon naught Q by R, right? That is the way we used to find the potential, right? So here we have applied that formula. Now you see we have already brought this Q1 here, so we must have due to Q1 there must be a potential at this point to which we are trying to bring this Q2. That is why we have found the potential first, then we are going to find work done now. So now work done to bring Q2 to the position R2, so let me write here R1 here, to the position R2, is W2 is equal to, that's going to be V1 into Q2, so that's going to be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12, right? R12. So let me write this R like this way, because once I have written this R in this way, right, then we're gonna write the R same way in each and every time when we're gonna use. Okay, if you have written the R this way once, then use that way only. Okay, don't change it. So now let me write here W2. This is W2. Okay, so now you see, now we are to bring Q3 to this position. Suppose this is the position vector R3, right? So here you see, in order to calculate the work done to bring Q3 from infinity to this position, we need to find the potential at this position due to these two charges. So now we have got Q2 here, and the distance between Q2 and Q3 is suppose R23. Let me write R23. So let me clean this, let me write it properly. This is the position, suppose Q3. Now this is the position R3, and distance from Q2 to Q3 is suppose R23, and distance from Q1 to Q3 is suppose R13. Let me write that way. Okay, so now potential due to Q1 and Q2 at R3, at the position vector R3, is, that's going to be given by V2 is equal to 1 by 4 pi epsilon naught Q1 by R13, and 1 by 4 pi epsilon naught Q2. So here the distance is represented by R23, distance between Q2 and Q3, right? So that is what we have got. So what going to be the work done? So work done to bring Q3 to R3 from infinity is given by W3 is equal to, so we have to multiply this one with Q3, right? So then what going to be the work done? Then the work done going to be equal to 1 by 4 pi epsilon naught. Let me take this term common. Okay, then we're gonna get Q1, so let me use another ink here, q1 q3 by r13, then plus q2 q3 by r13, right? That's what we have got. So then now let me write q1 q2 q3 sorry w1 w2 and w3 on the next page, because we have not enough space here. So what we have got w1 is equal to 0, so let me put it aside, okay, and w2 is equal to we have got 1 by 4 pi epsilon naught. So what was that? This one, right? So that is q1 q2 by r12, and w3, what we have got, w3. So this is w3, right? So w3 is going to be equal to, let me write this one, and here let me copy these things, okay. So this is the w3, so we have got this. So I have written the results so that I don't need to go the previous slide frequently, so that's why I have written this, okay. Now you see, so if we want to bring the fourth charge, we have already brought three charges, q1 q2 and q3, to their positions r1 r2 and r3, right? Now we are to bring q4 to this position r4, right? Then what going to be the work done? So then w4 will be equal to so let me write here, similarly we can write, so w4 going to be equal to this, right? And so on, right? So therefore total work done to bring all the charges, therefore total work done to bring all the charges q1 q2 qn to their positions is w is equal to, so net work done is equal to w1 plus w2 plus plus wn, right? And if we add all those, then what we're gonna get? We're gonna get 0 plus, then we're gonna have this w2 is equal to this one, right? So let me copy from here, this is w2, so this is the w2, and w3, this is the w3, let me copy this one as well, w3, this is w3, and just wait, let me clean this, and let me write the w4 here, this is w4, so this is just wait, let me rearrange this, okay. So here we're gonna have w4, this is w4, right? So now that's how we're gonna get, right? So what gonna be the wn? If you see the pattern, 1 by 4 pi epsilon naught, what gonna be the wn? You're gonna have q1 qn by r1n plus q2 qn by r2n, then plus q3 qn by r3n, right? That's what we're gonna have. Let me write here 2n plus ... so on. That's what we're gonna have, right? So now here you can see that let me rearrange it. Now let me take common all these terms, 1 by 4 pi epsilon naught, from all this from all the terms we can take this common, right? So let me take that way. So if we do take common, okay, now let me copy these things and let me go to the new slide, okay. Let me copy these things. So this is w net, okay, Now let me copy these things and let me go to the new slide. Okay, so here you see, so taking all this 4 pi epsilon not common, so what we can write, so we can write here, let me take this common, so then within bracket what we're going to write, so q1 q2 by r1 r2, q1 q2 by r1 r2, then q1 q3 by r1 r3, we can write q1 q3 by r1 3, plus then similarly q1 q4 by r1 4, and plus dot so on up to this q1 qn by r1n, plus similarly we're gonna start with q2 q3 by r23, plus then q2 q4 by r24, then plus dot so on up to q2 qn by 2n, right, up to q2 qn by r2n, and plus then again what we're gonna write, then again we start with q3, right, q3 qn by r3n, here it should be, when we gonna start 3 then it should be 4, okay. 1 2 we start with 1 2, then when we start with q2 then q2 3, then similarly so q1 and q2, right, then when you start with q2 then another source should be q3, when you start with q3 then other source should be q4. So hope you can observe this pattern, right, just observe it carefully. Okay, plus dot up to q q3 qn by r3n, right, plus dot so on. So when we're gonna start with qn minus 1, then we gonna have here qn, the other source should be qn, and here are n minus 1 and n, right, rn minus 1 and n. So hope you have understood this. Let me write this way, just let me write it properly, rn minus 1 and n, right. So here you see how we have got this, because you see when you observe here, when you have start with q1 then the other source start with q2, similarly this is q1 q3, so if the last term is qn, last charge is qn, then the charge before the last one which is brought to its respective position is qn minus 1, right. If this is the nth term, charge, then it must be the n minus 1 charge, right. So hope you have understood this. If you see the numbers with the charges, here you see this one is less than this one, right. Here you can see the starting part, this one is less than this one by 1, right. Similarly when you start 2, this one is less than this one, right. So now you see, so we have taken qn charges, so this is gonna be the last term, right. So we cannot have qn plus 1 term, because we have taken only qn charges, n number of charges, so up to qn, so we can end here, right. So let me cut it. So here you see, so it can be written in the form of summation in this way, 1 by 4 pi epsilon naught. So here summation from I is equal to 1 up to n minus 1, right, up to n minus 1, this one here you see last time, this is n minus 1 qi, Okay, so here we have put q1 q2 up from I is equal to 1 to up to q here n minus 1, right? So hope you have understood this. Then into qj, okay, j, so the second charge, so which is this 2 is 1 plus 1, right? This is 1, right? So we can see, and this one is 1 plus 2, 1 plus 2. So similarly here you see this j is nothing but I plus 1, right? Okay, I plus 1, because here you see this is n minus 1, so you can say n minus 1 is I and this one is j, so then n minus 1 plus 1, that's going to be n, right? So hope you have understood this, right? So and j goes to n, and I goes to n minus 1, right? So hope you have understood this. So this is the, this is the work done, total work done, and this is going to be the energy, electrostatic energy. Let me write this one on the other side. Okay, just wait, let me copy this result. This work done that we have got, net work done or total work done we have got, that gonna be equal to the potential energy, right? So that's gonna be equal to this potential energy of system of n charges, right? System of n charges. Okay, so this is the expression for electric potential energy of a system of charges, right? That's how we can obtain the required expression. So now you see, just wait. So what is the last part of the question? Let me go back to the question. Just pause the video and note all these things. So this is the previous slide, and this is the next previous slide. This one. This is the second slide. This is first, second, third, fourth, and fifth. So these are the slides. Okay, here you see this is the last part of the question. So that energy density is given by this expression. Let me go to a new slide. Before going to that, I'm going to show you all the slides again. This is the first one, the first slide of this answer. This question number 3A. This is the first slide where we have started writing 3A answer. This is the second, and this is the third slide. This is the fourth slide, and this is the fifth slide. So now let me prove that. Now we are to prove that U is equal to this epsilon naught by 2 E square. So here you see, and I forgot to mention one thing: epsilon naught, meaning of the epsilon naught, and this is permittivity of free space. And here electric, this is E is electric field intensity. So now let us prove this one. How to prove this? So now you see, capacitance of we know that capacitance of a capacitor is given by C is equal to epsilon naught A by D. So here you see what is A and what is D here. D be the separation between the capacitor plates, and A is the area of each plate, right? So what we're gonna write, D is the separation between the plates of the capacitor, and A is the area of its plate, right? Its plate. And also we know that U is equal to Q square divided by 2C, right? Divided by 2C. And where Q is charge on its plate, so area of its plate with charge, we can write here with charges Q, right? So in that case, what we're going to do here, electric field E is equal to, that is Q by A epsilon naught, right? Q by A epsilon naught. So now let us use let me take this as equation number 1, let me take this as equation number 2, and this is 3, right? Just wait, this is 3. So let me copy these equations and let me go to a new slide, so where we can simplify. So these are the equations, okay? So now let us using 3 and 1 in 2. So then we're gonna get U is equal to, instead of Q square we're gonna have, so here from this equation number 3, what we're gonna have, you're gonna get Q is equal to into A epsilon naught, right? So we're gonna have E A epsilon naught whole square divided by 2C. Instead of C we're gonna put this, right? Epsilon naught A by D. That's what we're gonna get, right? Here let me tell you one more thing. This U represents electric potential energy, but we are to prove this one. Let me write this capital U, okay? This capital U represents potential energy density, okay? Electrostatic potential energy density. So this capital U is nothing but small u by volume, okay? So electrostatic potential energy per unit volume. So let me consider that way, okay? So here you see, and therefore energy density let me write here capital U, okay? So let me go to the previous slide. Here you see this small u, this one represents electric potential energy. This is electric potential energy, and this represents electric potential energy density. This is energy density, right? So hope you have understood, and this is equal to small u by volume, okay? So now here you see, first so what gonna be the volume? Here you see, if I have said that this is the area A and separation between these two is small d, then volume is given by A into D, right? So here we're gonna write A into D. So first let me simplify these things. Here E square A square epsilon naught square divided by 2, and this D goes up, here it's gonna be D 2 epsilon naught A, and after cancellation what we're gonna have, E square, this A cancels A square to give A, and epsilon cancels epsilon naught square to give epsilon naught. So here we're gonna have E A epsilon naught into D. Let me write the D first, okay? Here we're gonna get D by 2. That's what we're gonna have. So from here let us put here to find energy density, that is capital U, E A into D epsilon naught by, here we have A into D, that is volume, right? A into D. So here AD cancels. So what we have got, sorry, I forgot to write the 2 here, divided by 2. So capital U, that is equal to 1 by 2 epsilon naught E square. That is what we needed to show, right? Hence proof. So hope you have understood this. Now let us solve question number 3b. So here we have two options. Either we need to solve this one or this one. I'm going to show you both. First one, the capacitance of a parallel plate capacitor is 400 picofarad and the plates are separated by 2 mm of air. What will be the energy when it is charged to 1500 volt? What will be the potential difference with the same charge if the plate separation is doubled? Okay, so let us solve this question first. So first let me solve this one. So let me write the given things here. So capacitance is 400 picofarad. 400 picofarad. So let it convert it to farad. That's going to be 400 into 10 to the power minus 12 farad, right? So and separation between the plates is given by 2 mm. Here it is given 2 mm, so which is going to be equal to 2 into 10 to the power minus 3 meter, right? And voltage potential difference is 1500 here, 1500 volt. Okay, so what gonna be the energy? Okay, so what will be the what is the question here? What will be the energy when the charged when the plates are charged up to 1500 volt, right? So here you see, let me write the find the energy. Okay, so here we're going to use this formula. U is equal to half CV square. Okay, so if we use that formula, then what we're going to have, so let's put the values here. 1 by 2 capacitance is given 400 into 10 to the power minus 12, and voltage is 1500 here. Charge here you see potential is 1500 here. So we're going to write here 1500 square. So now, so here you see this unit going to be joule, and if you calculate this, that's going to be 200 and 200 into 10 to the power minus 12, and squaring 1500, we're going to get 225 4 zeros, and then if you multiply all this, here you see 4 zeros, 2 zeros, 6 zeros, so it can be neutralized with this. If we do so, then what we're going to get, so here U will be equal to 2 into 225 into 10 to the power minus 6, as we have here 6 zeros, right? So hope you have understood these things. If you multiply, then you can write this going to be 450 into 10 to the power minus 6 joule, and it can be written 4.5 into 10 to the power minus 4 joule, right? If you write the answer in scientific form, this is the energy. So we have got the energy, right? So what will be the potential difference? So what going to be V, right? If the same charge plate separation is doubled, if this separation is doubled, then what going to be the potential? So let's find that one first. So here you see, just wait, let me clear this, and let me write this part here above. Just wait. Now let's move on to next part. This is the answer of the first part. Energy we have got. What will be the potential difference with the same charge? Okay. Charge is same. What will be the potential difference if plate separation is doubled? So now, if plate separation is doubled, so initially it was D, now it becomes suppose 2D, right? and we know that capacitance C is equal to epsilon naught A by 2D. Then new capacitance C dash will be equal to epsilon naught A by twice D, right? So here we have to write D dash, and if you replace D dash by this, then what you're gonna have, C dash is equal to epsilon naught, right? Epsilon naught A by, instead of D dash we're gonna have 2D, right? And if that is the case, then what we can write, that therefore C dash is equal to, so here you can see, if you compare these two, right, then what you gonna get? So this part is nothing but your C, right? So C will be equal to C dash will be equal to half of C. That's what we will get, right? Now charge is seen. Q is equal to, we know that Q is equal to, let me write here, Q is equal to C into V, right? So which implies V is equal to Q by C. Again, for same charge, we're gonna have Q dash, sorry, not Q dash, Q charge is same, that's why C dash and V dash, right? So C dash is equal to half of C, so you're gonna put half of C dash, instead of C dash, here we can write Q is equal to, instead of C dash we're gonna put, let me write these things, so let me write here, Q is equal to C dash V dash, and C dash is half of C, and V dash is 2 times of, sorry, let me keep the V dash as V dash. So here you see, if you simplify this, then you're gonna have V dash is equal to 2QC, and 2QC is nothing but 2 into V, right? V is equal to Q by C, right? So we're gonna get here 2 into V, right? So now you see, so if that is the case, then 2 into V is, here we have got 1500 volt. If you put 1500 volt here, then it's gonna be equal to 3000 volt, right? So this is gonna be the answer, right? So if charge is same and separation is double, then the potential difference V dash gonna be equal to 2 times, right? So hope you have understood this. So now let's move on to the next part. There was another question of 3b, which is either we have to solve this one or that one. So let me show that one. So this is the next equation, 3b, or find the expression for the capacitance per unit length of the capacitor consisting of 2 coaxial cylinders. Okay, let me solve this one. So here this is 3b or answer, right? So expression for capacitance per unit length of 2 capacitor consisting 2 coaxial capacitor. So here we have suppose 2 capacitors, one capacitor with a 2 coaxial cylinder, and radius of the inner one is suppose small a, and radius of the outer one is suppose small b. Let me take this one as a small b. This radius is a small b. Let me write this way. This is a small b. Okay. So now these are charged with positive q and negative q charge, right? Let me take that way, and its length is suppose L. Let me take the length is L here, right? Okay, so let me write here, let us consider 2 coaxial cylinders. Just let me write here, let us consider a capacitor of consisting two coaxial cylinders of length L. Okay, let their radii or just wait, let me write this way. Let A be the radius of inner cylinder and B be the radius of outer cylinder. Let me consider that way. And lambda is the charge per unit length. That is Q by L. So if I have considered here capital Q, then it's going to be capital Q, right? Okay, so capital Q is the charge on its plate, its cylinder. Okay, so let me take that way. Now we know that electric field. Here we know that electric field due to a infinitely long charged cylinder at a distance r is given by E is equal to lambda by 2 pi epsilon naught into r, or you can write 2 pi r into epsilon naught. You can write that. Okay, and so here you see, therefore potential difference. So then in that case, potential difference between the cylinders. So if these two are, if you assume these two are infinitely long cylinders, then what gonna be the the potential difference between the two cylinders if infinitely long, right, then we can write V is equal to minus integration from A to B. Inner radius is A and outer radius is B, so A to B, so E dr, right, E dr. So now let me put this one here and then let us integrate this. So let me copy these things and let me go to the new slide. Okay, so here you see, this is what we have. So now V is equal to minus integration from A to B lambda by epsilon naught, lambda by 2 pi r epsilon naught dr. That's what we're gonna get. so E is replaced by this, right? So then lambda is constant here, lambda by 2 pi epsilon naught, this part is constant, and here we have 1 by r dr. If you integrate this, then what it gonna be? It gonna be equal to what? Integration of 1 by r, that's log, right? So here we're gonna write natural log, so ln, we're gonna write ln here, pi by 2 pi epsilon naught, lambda by 2 pi epsilon naught, and here it's gonna be ln r, okay, that is log r, and we are integrating it from a to b, and if you put the upper and lower limits, then what it gonna be? It's gonna be minus lambda pi 2 pi epsilon naught, and it's gonna be equal to ln log a minus natural log b, right? And if you multiply this minus sign, so it's gonna be natural log b, and here it's gonna be a if you make it positive, right? And we know log m minus log n is log m by a, m by n, so we have got that property, log m minus log n is equal to log m by n, right? If we use that property, so this is ln is nothing but natural log, that means if the base is e, then we used to write let me write it. So here lambda by 2 pi epsilon naught, we have got ln b by a, that's what we have got. So now capacitance, we know capacitance is given by C is equal to Q by V. Here potential we have got this, right? And charge, so for charge per unit length is lambda, then total charge gonna be for length L, that gonna be lambda into L. So here we're gonna get, okay, capacitance of length L, we're gonna get C is equal to lambda by lambda into L by the potential difference, that is lambda by 2 pi epsilon naught natural log b by a, that's what we're gonna have. So here lambda cancels, so it's gonna be equal to 2 pi epsilon naught L, that is length L in divided by ln b by a, and therefore capacitance per unit length, therefore capacitance per unit length, that gonna be C by L. So if you divide this one by L, this L will be cancelled, right? Then the result gonna be this, right? So this is our answer. So hope you have understood this. So thank you for watching, and remaining questions will be solved in the next part. Okay, when next part will be uploaded, that gonna be appearing at the end of this video, at the end screen. So you have to wait for that because I'm gonna upload it maybe after 2-3 days. Okay,